The following is a production of Texas Lutheran University. For more information, please visit tlu.edu.
Our speaker today is one of our own, Dr. Alison. Bray teaches in the chemistry department. Dr. Bray has a Bachelor of Arts in Chemistry with an emphasis in biochemistry and marine science from the University of San Diego. She holds a Master's of Science in Earth Sciences with a specialty in geochemical systems from the University of New Hampshire, and she earned her PhD in the topic of earth sciences from the University of New Hampshire. Dr. Bray not only has a pretty stellar academic background, but she has had experience working as an environmental consultant. For 5 years, she worked out of Newburyport, Massachusetts, in an environmental consulting firm. And today she's going to talk about something very interesting to her. She's going to tell us about going down to deep water, deep ocean vents, and some of the things you might be able to see down there. So please welcome Dr. Alison Bray.
Thank you. Which lights do you want to turn off? Can you all hear me? Okay. So yes, I'm going to talk about something that's near and dear to my heart today. Some of you have heard little bits of this in some classes because I'm very excited about it and I stick it in where I can. But this is what I worked on in graduate school. I went from San Diego, where I had been working as an undergrad chemist, working on some environmental things, to something completely different and working in deep sea exploration and deep sea chemistry. And that was what I got my PhD in, was the chemistry of deep sea hot springs. So that is what we're going to talk about today. We're going to talk about it in a pretty broad sense, in that we're going to talk about some of the geology, the chemistry, and I'm going to tread into dangerous territory for myself and even talk about the biology. So I am not a biologist, but I'll do my best, okay? So today, between the devil and the deep blue sea. Come on, clicker. There we go. So what we're going to talk about, just to give you the big picture before we start, we're going to talk about why are we studying the oceans? Why do we care? And then we're going to do a quick review of marine geology for any and all of you that haven't had marine geology before. Then we're going to take this completely tangent side trip and talk about submersibles and deep sea diving. And then finally, we'll get back to deep sea hot springs, which, as you'll find out, is a home of very exciting chemistry and some really amazing critters. Okay? So it's a three-part story. Deep sea hot springs, you can't be just a chemist, just a geologist, or just a biologist. You kind of have to play it from all angles, okay? It's all these systems combined, very multidisciplinary. So first, here's the 30-second overview of the history of oceanography, okay? We'll sum up, a couple thousand years here in 30 seconds. Oceans, water, they're important to all of us, right? I mean, we're mostly water. We can get along without food. We cannot get along without water. The oceans have been important since the time before Christ, okay? The Phoenicians actually had a navy in the Mediterranean many, 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 many years ago. In the 1400s, the Chinese went exploring during peacetime. However, they weren't going for the purposes of studying oceanography particularly. They were going to find trade routes and just happened to be out cruising the oceans and looking at things that they observed on the way. It wasn't until the 1800s that we really got serious about starting to look at the oceans from a scientific perspective, okay? Trying to figure out what's there, why it's there, measuring how much, how deep, and then tracking, looking at all the different life forms, things that were probably called mermaids and sea dragons at one time, actually cataloging those and figuring out what they were. Ironically, here we are 150 years later, and we're still working on that same set of questions, which doesn't speak badly of oceanographers. It's just that the ocean's really big, and every question opens a whole new can of worms of questions. So that was it, 30 seconds, oceanography. Okay, let's talk about the Earth. Okay, the Earth is where we live, of course. It's mostly water on the surface, but we need to think about what's within the Earth. The Earth is made up of a set of concentric spheres, okay? This is a little cutaway. This is the pretty cutaway. If we were to take a slice out of the Earth, we would see that the atmosphere way up there, the crust, that's where we live, right? The solid part that we are standing on. the mantle below it, which is semi-squishy. It's not liquid, but it's like silly putty. And then the outer core, which is liquid, and the inner core, which is solid. So what we're going to be most interested in talking about today is the crust. Okay, here's the continental crust, the part we live on. There's actually crust under the oceans as well, okay? But it's much thinner and it's different in composition than the crust we find generally on land. The crust on land is mostly granitic, very low in iron and manganese, whereas oceanic crust tends to be much more rich in iron, much darker sorts of rocks. Most ocean rocks are dark black, okay? The other part we're going to be interested in is this little thing in here called the asthenosphere. It's part of the upper mantle. It's hot, okay? Think like 1600 degrees Celsius, 1000 degrees Celsius. So at that point, rocks are not liquefied. They're not quite melted yet, but they're ductile. They can move, okay? Slow, silly putty, viscous movement. And in fact, our crust actually floats, if you will, on the asthenosphere. And that's going to become important in a moment. Okay, so today we're going to focus on the oceanic crust. We don't care about the continental crust. We just know that it's there and we can stand on it. Okay. Anyone remember this picture from 5th grade science? Good old Pangea. Okay, so the idea of Pangea and that all the continents at one point were in a different place was proposed by Alfred Wegener around 1912. But he was written off as loopy, pretty much. Nobody bought it. How on earth, I mean, how could you even envision, considering at that point, of course, we hadn't seen the Earth from space, how could you even imagine that things the size of continents were moving around and floating into different positions? But we had evidence, primarily from biology, of things that matched up. Fossils from South America that matched up with fossils in Africa. Rocks of similar types that looked remarkably like the rocks over here. Same thing up in North America and these plates up here. Okay, so the evidence was there, but nobody bought it. It was dismissed. Luckily for him, he is still remembered in history because it really was his idea. It wasn't until 1960, so many years later, that Harry Hess came up with the idea of why it really was possible for the crust to be moving around and for the continents to move from one place to another. And he called this the idea of seafloor spreading, okay? He suggested that seafloor, new seafloor, brand new oceanic crust, was being formed somewhere, and he called it the mid-ocean ridge. He knew from them laying telegraph cables across the Atlantic, everyone knew that there was a mountain chain out in the middle of the Atlantic. Flat, 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 big mountain chain, back to flat. Because they ran into a lot of trouble when they were trying to set up the original telegraph cables. They ran into this mountain chain that no one was expecting. Okay? So he suggested that they were actually volcanic and that there was new crust being formed right there. He said the continents were being pushed apart as new crust was forming. Okay? And that was pushing the continents around. And he went even further and he said that the motion was powered by heat convection. Heat rises, yes, heat rises. It gets to a point where it can't go any higher and then starts to cool down and sink. He said that the motion of the crust was actually coming from these currents in the asthenosphere. And remember, the asthenosphere was what? Kind of Play-Doh-y, not liquid, but movable, okay? So the continents were actually surfing and moving on convection currents within the asthenosphere. Keep in mind that in 1960, these tools were still pretty primitive. We weren't really, diving regularly to the bottom of the sea to see any of this stuff. This was all done from the surface and observations in a few cases where they were dragging cameras or a few other things behind ships. But mostly it was like throw a bucket over the side and drag up some rocks and see what you could figure out from that. Okay, so the theory of plate tectonics, again, many of you probably saw this way back in 5th or 6th grade science. The crust is divided into a series of lithospheric plates, superficial plates. The plates are moving apart, being pushed apart at the mid-ocean ridge. Magma, hot melted rock coming from deeper in the mantle, comes up, fills in the holes, cools, and makes new hard crust. pushes out to the side, and this process repeats and repeats and repeats. So where does all the old crust go? If we're making new crust and the Earth isn't getting bigger, it's got to go somewhere, right? We can't just keep adding infinitely. So the formation of new oceanic crust is balanced by the process of subduction, sucking of old crust down underneath the continental plates, where it gets remelted and recycled back into the system. And we'll look at this in picture form in a minute. And again, the driving force, what's making this happen, is the convection in the asthenosphere, the heat convection. So let's look at it in a picture form. Here we are, right here, that's us right there in Texas, floating along on the continental crust. Here we have the convection currents, okay, the heat in the mantle, heat in the upper mantle, the asthenosphere. And we have places, say this is the Atlantic Ocean, where the mid-ocean, one of the mid-ocean ridges is. Up flows new lava, pushes up, pushes this crust over, makes new hard rock in the middle, pushes this continental crust over to the left. At the same time, over in the Pacific, old crust is being forced down underneath the continental crust by gravity and just by brute force, and being remelted into the asthenosphere. What do we know about the area around the Pacific Ocean? Anything exciting ever happen around the Pacific Rim? Earthquakes, volcanoes, generally bad from a human perspective, okay? That's because of all this that's going on. That crust, it looks so smooth and pretty in diagram form. There's nothing smooth and pretty about shoving one rock under another rock and remelting it, okay? So in this area, you're going to get all sorts of exciting things, earthquakes, volcanoes, and other things. The Ring of Fire in the Pacific. It's not the only place it happens, but that's the best example. So these are the plates as we see them today, okay? We live here on the North American plate. California is actually split. There's the Wanafuka plate is right here, and those plates are not moving apart from each other. They are sliding past one another. So California is actually, or a portion of California is actually moving north, and someday we'll end up in Alaska, long after we're gone, okay? So this is the arrangement now. This will not be the arrangement in 1 million, 2 million, 5 million years. So types of plate boundaries. We've already hit on this a little bit. A divergent plate, plates boundary where plates are coming apart and we're making new crust. A convergent boundary, plates are slamming into each other. If it's two pieces of continental crust slamming into each other, continental crust would have the same density, so nobody gets forced under. Best example of that would be the Himalayas. What happens in the Himalayas? Crust comes together and nobody sinks. Where does it go? Up. And that's how the Himalayas are built. And then the other one would be a transform plate, the sliding past, like the California situation. Again, what happens in California? Earthquakes, right? Those plates are slipping past each other, and while we'd like to think that it's a smooth and easy process, it's not. I'm not a fan of the earthquake. Okay. So today we're really going to talk about divergent plates, right? Because we're in the ocean and we're looking at a place where new crust is being formed. Okay. The divergent plate boundary. We have two plates moving apart, new crust being formed, and the crust, as the magma comes up, the hot lava, melted rock from deep within the earth, pushes up and actually cracks the new crust that's up there and fills in the holes. You can imagine this is a fairly violent process, right? Rock, splitting rock, okay? And we get new ocean crust. As that crust moves away from the center, it starts to cool, it becomes less dense, and it will start to sink down. So we have a mountain in the middle, and it sinks out towards the edges. Okay? So if we look at this is a South America and Africa at one point, right? From the old Pangea picture, we know that they were together. Upwelling of hot molten rock, warping of the crust, stretching to the point that eventually it breaks. Up comes the magma, fills in these gaps, and that process repeats and repeats until South America and Africa have literally been pushed apart. Okay? And in the middle, we now have the proto-Atlantic. Okay? It filled in with water. Now that space is fairly big, right? That process is still occurring. New crust is still being formed right here at the mid-ocean ridge. How fast is this happening? Well, it depends on where you go. Okay? If you go to the mid-Atlantic ridge, so out in the middle of the Atlantic, it's going really, really slow, like half a centimeter a year. Okay? If you go to the East Pacific Rise, in the northern East Pacific Rise, so off the coast of Mexico, about 6 centimeters a year, which doesn't seem like a lot, but if you think about that on a geologic Earth scale, 6 centimeters a year is, well, 6 centimeters. Where's our centimeters here? So like that much? And that's really a lot for the Earth. If you go down to the southern East Pacific Rise off the coast of South America, it's cruising. That's the fastest spreading ridge we have, 11 centimeters per year. The mid-Indian Ridge is just now being explored. It looks like it's sort of middling, 1.5 to 3.5. And people are even starting to explore the ridges that are under the ice, under the polar ice caps. Those appear to move very slowly. On land, the East African Rift Valley, if you're familiar with that, is actually a place where this is happening. Continental crust is being pulled apart, and there's volcanic activity there. So eventually, East Africa may be pushed away from the mainland. Probably, again, not in our lifetime. If you want to go see the ridge and stand on it, or say I stood on the North American plate and then I stood on the Eurasian plate, you have to go to Iceland, because Iceland is the only place where the ridge comes up above sea level for us to see, other than the East African ridge. Okay, so here's our mid-Atlantic ridge. Here's Canada. Well, there's Canada. There's Boston, and then, you know, Texas somewhere over here. Okay, so you can go to Iceland and you can actually go and explore these volcanoes. This is why Iceland is so volcanic, violently volcanic, because we have a whole chain of volcanoes running right through it as those plates are pushing apart. So Iceland is getting pushed apart, split in half by the formation. I guess we're making more Iceland, really. Iceland is growing as a country physically. Okay? It's very, very active, right? What was it, earlier last October, I think? The airports in Europe were shut down because of all the ash that was spewing off of Iceland. So this is an ongoing process. Okay. We're going to end geology for a moment. Switch, chemistry. Okay? 7 major elements comprise 99% of seawater. Seawater is salty, yes? Wouldn't want to drink it. Most of it is sodium and chloride. Okay? A little bit of sulfate, some magnesium, some potassium, some calcium, and a little bicarbonate running around. Those 7 make up 99% of what we consider seawater to be the salt in seawater. Most of the time we just deal with sodium chloride, table salt, but actually these have a decent concentration as well. If you wanted to, and you had the whole periodic table to work with and all the time in the world, you would actually be able to find just about every element, naturally occurring element, that's in the crust in the atmosphere at some level in the ocean. All depends on how good your instruments are and how low you can read. We consider those to be minor elements, or if they're really low, parts per billion level, trace elements. We say that the oceans are at dynamic equilibrium. Those of you taking analytical right now, I'm sure love the term equilibrium. Okay? Same idea. The concentration of the ocean, the salty factor of the ocean, isn't changing much. It hasn't changed much in human terms. Okay? Maybe in a few places it's gotten a little more salty, a little less salty, but overall the salinity is fairly constant around the world and fairly constant over time. Okay? That tells us that the rate of chemicals coming into the ocean has to be somehow balanced by the rate of chemicals going out of the ocean. If it wasn't, what would happen? If we were just dumping chemicals in through rivers and rain, eventually would the ocean get more salty? Okay, but it's not. So why? Why is that not happening? So oceanographers love to balance budgets. Okay? How much of an element goes into the ocean and how much goes out? If we really are at chemical equilibrium, the inflow, or the sources, the inflow being primarily from rivers, runoff from rivers, has to be balanced by some outflow. You got to balance your checkbook, balance the budget. Congress should come be an oceanographer for a while. Talk about balancing a budget. Okay, we have to figure out how the inflows balance the outflows. So here's the question. We've been trying to do this. What I said, oceanography, 150 years of trying to answer these questions. And for some elements, pretty close. Quantitatively, we can say this much potassium comes out of the rivers. We know where the potassium is going in the ocean, and that's why the ocean has this concentration of potassium all the time. For some elements, that can be done. The one that was mysterious, really mysterious, was magnesium. Nobody could figure out how to mathematically balance all the magnesium that was coming out of rivers with the magnesium concentration in the ocean. Why wasn't the magnesium concentration continually going up? Because no one could find where that magnesium was going. There was a missing sink, a missing exit point, okay? And it had to be big. It couldn't be, this wasn't like we were off by a little bit. It was like a huge chunk that we needed to get rid of. So where is that missing sink? Well, it took a while to figure it out. Now we're getting into my lifetime, so this is recent history, okay? In 1972, people were dragging camera sleds along the bottom. A big, think of it literally as a big metal sled with a bunch of cameras and probably some temperature probes and some sort of seismometer to measure earthquakes. And they were dragging it behind their ship near the Galapagos Ridge, which is right off of the Galapagos Islands in the Pacific, and they saw some funny things that they weren't necessarily expecting. They saw these little seafloor mounds, mounds of little tiny mountains. They had a ton of earthquake activity, like 80 earthquakes in a minute or something ridiculous. It was really high. And they saw a very slight, on their temperature probe, they saw these little blips in temperature, bigger than the noise of normal dragging your temperature probe through the ocean. In general, the bottom of the ocean is about 2 degrees Celsius. And they were seeing tiny elevations in temperature, probably on the order of a couple tenths of a degree. So not much. But at least they got wheels spinning. Something was going on. So finally, in 1977, they found the answer. They went back to that same spot with a submarine, this little submarine here that we'll talk about in a minute, and they found the first warm water springs coming up out of the bottom of the sea. This was very exciting. Nobody had ever seen this before. We've seen hot springs before, right? Where geysers on land, but no one had actually ever seen this on the bottom of the ocean. Suspected they were there because clearly we were missing something from a chemical point of view, but no one had ever seen them in person. What did they find? Well, not only did they find these warm waters percolating out of the bottom of the seafloor, they found animals that no one had ever dreamed of. And ironically, on that cruise in 1977, it was a bunch of geologists and a bunch of chemists. There was nary a biologist on board. Because the ocean's a vast, empty desert, right? Nothing out there, nothing living there. So there were no biologists on board. So you had a bunch of chemists and geologists finding giant clams that were a foot long, and I'm sure somehow telegraphing at that point, probably, back to land saying, hey, we found 1-foot clams, and a bunch of biologists saying, yeah, right. Well, they did. They dragged them up and brought them home. The next major discovery happened at 21 degrees north on the East Pacific Rise, near the Galapagos, but a little bit farther south. So when they got there, they actually found vents, deep sea hot springs with temperatures up to 350 degrees Celsius. 350 degrees Celsius, bottom seawater, 2 degrees Celsius. This is really hot. But that wasn't what was exciting. I mean, that's exciting in itself. But the really cool thing was that these fluids had no magnesium in them, like 0. So we know that seawater has about 52 millimoles per liter of magnesium. So this was the sink. This must be where all that magnesium is going. And we'll talk about why in a moment. So this was big. 1977 to 1979 were huge years of discovery. Totally turned oceanography upside down. This is the first photographed picture of a high temperature deep sea hot spring taken at 21 North in 1979. Okay, so the picture quality has greatly improved over the years. This was taken through a window with a 35 millimeter film camera through a plexiglass window. Okay, so now time for our quick side trip. All right, we're going to talk about what they were using to get there. They used the deep submergence vehicle Alvin. Okay, Alvin was designed by the US Navy for rescue purposes and secret missions, Navy type things, not for science. But then they realized that really they didn't have all that many uses for it and that maybe it would be really useful for science. So most of the time Alvin is lent or rented to the scientists to use for science. On occasion the Navy calls when they're in a pickle and says, we need Alvin and we need it now, drop what you're doing and bring it. Okay? So Alvin was the first human-occupied US submarine. It's been diving since 1964, but didn't dive on the vents until 1979, and has well over 4,000 dives. It is untethered. Okay? There's no string attached. It's free to drive about where it wants. It can dive as deep as 4,500 meters, but typically dives are more like 2,000 meters, so about 8,000-ish feet. The Alvin, here's Alvin here. What you can't see, got cut off from the bottom of my little slide here, is the Trieste. The Trieste was also it was a tethered bathyscape type thing. It was like a metal box on a string. Was lowered into the Marianas Trench, which is the deepest point in the ocean. Okay? No one has ever been back to the Marianas Trench until last week, literally. James Cameron, director of Titanic and other great movies, built his own submersible and many, many years later returned to the Marianas Trench. It's taken that many years to get back. Okay? Alvin cannot dive into the Marianas Trench. It's too deep. It exceeds its safety limit. But really, most people want to dive on the ridges, which are only about 2,500 meters. So, human-occupied vehicle, or an HOV. It's the most famous, some of its more famous discoveries. The Navy used it once when they, lost a hydrogen bomb off the coast of Spain and didn't really want anyone to know. I was reading about this story, and they had all these submarines out there looking for it, but they wouldn't tell them what the bomb looked like. Can you go find the bomb, but we're not going to tell you what it looks like. Alvin found it, and that was like a big triumph for Alvin, because it's kind of funny looking, right? It doesn't look very sciencey, and it looked even less sciencey back in the 60s, okay? But Alvin showed how useful it was when it found and actually recovered the hydrogen bomb. It actually located and surveyed the wreck of the Titanic in 1986. That location was meant to be kept a secret. The scientists, it was American scientists that discovered it. They intended for the location not to be revealed for the sake of it being a graveyard. Unfortunately, that didn't happen. So now everyone knows where the Titanic is because we all saw it in James Cameron's movie, right? The Titanic footage was not filmed with Alvin. It was filmed with Russian. The Russians have 2 submarines, and they used that for filming. And most recently, they actually called Alvin up when the Deepwater Horizon blowout occurred to go down and survey some of the damage, and especially the ecological damage. Okay? Why is it called Alvin? It's truly not the chipmunk. It was named after Alan Vine, who, this was his idea way, way back from his very days in college. He had this idea that he watched oceanographers dragging their stuff behind their boats and throwing things over the side and said, well, why can't we go there? Why can't we do this? And it took him a long time to convince anyone we could. Alan Vine passed away, I think, in 1994. He would say it was named after the chipmunk, but Alvin actually means noble friend or loyal friend or something, so it's an appropriate name either way. Working in the deep sea, it's not easy. It's fun, but not easy, okay? imagine this. It's dark. Bottom of the ocean is dark. There's no light. They don't turn the lights on until you're about a foot off the bottom, 2 or 3 feet off the bottom. You're stuffed in a 6-foot metal sphere with now 2 of your closest friends. A pilot and 2 scientists can fit in the sphere. You're sitting on an active volcano most of the time. And you have 350 degrees Celsius water next to your porthole, which is made out of plexiglass, which melts at probably 65 degrees. Yeah. So you also know, because you've been lectured on it before you left, that there's no plan B. If something goes wrong, you have 216 hours of oxygen and no rescue plan. So everyone goes anyway, right? Wouldn't you go, despite all that? Okay. Alvin can be equipped with just about anything you want to stick on it, provided that you can prove that it doesn't implode under pressure. To give you an idea of what the pressure is like when you're diving on the ridge at 2,500 meters, nobody has these anymore. Wig heads, where women used to put their styrofoam heads, they put their wigs on them. So this was about the size of a human head. This went down on the outside of the submarine, and this is the size it ended up as. I colored it before it went. A styrofoam coffee cup. I had to tape 2 cups together because I couldn't find a decent one upstairs of the right size. About that size, came back about that size. Okay, so those went in a mesh bag outside the submarine. So do you want to be outside the submarine? No. Okay, so you have to prove that your tools, your cameras, your shrimp slurp guns for slurping up shrimp are not going to implode or cause any damage. They've taken the IMAX cameras down. IMAX cameras are huge and heavy. They had to pretty much strip everything off of Alvin and just to put the IMAX cameras on. They have video cameras, still cameras. They probably, when I stopped diving, we were still on film cameras. I'm sure it's all digital now. Okay? Anything you send down has to be able to be tolerated by the pressure and the temperature and the corrosion factor of sitting in salt water. This is a little schematic of kind of what the inside of Alvin looks like. It makes it look roomier than it is. So you have your pilot crouched down here. That's you, one of the scientists over there, another scientist over there. You have about a window the size of a softball to look out. And it's plexiglass that's it's conical, but it's about that thick. So your view is a little distorted. Okay? At the moment, right after the Deepwater Horizon, that was its last mission, Alvin has been beached since 2011 and is currently undergoing a huge overhaul. Normally they take it out of the water every 3 years and put it back together from bolt number 1 to bolt number 375. This time it's getting a huge overhaul. They're actually getting a new sphere so it can go deeper, better batteries. I think they're going to put a computer in that is of this century. Alvin, not that, well, up until now, really has still had fuses and all sorts of archaic things that we kept using because they kept working. Okay, so it's our workhorse of the deep. So we've used Alvin plus some remotely operated vehicles, things, robots on tethers, to go find new hydrothermal sites after they found 21 North, and it was like a heyday. Let's go see what we can find. And then we have sites that we've returned to over and over again for long-term studies. Okay, so let's return to what we were talking about before, these deep-sea hot springs. And sometimes in National Geographic, you see them referred to as black smokers because they look like they're smoking black gunk out into the ocean. The on-land equivalents, like I said before, geysers, if you've ever been to the Salton Sea or if you've been to Iceland or Yellowstone, you've seen geysers. Same idea, water being heated by hot rocks and coming up out of the ocean floor. So how is this working? This is the very simplified drawing of what's going on. Remember we said that we had hot rocks because we're sitting on a volcano where new ocean crust is being formed, and we have 2 degrees Celsius seawater. Well, oceanic crust looks kind of like Swiss cheese in composition. It's got holes and crevices and breaks and cracks. So seawater can actually flow down into those holes and cracks. And all along the way, it's reacting at various temperatures with the rock around it. And its chemistry is changing. Eventually, one of two things happens. Either it gets to the point where the rock is not solid enough for water to flow through. You have to have some channels. It has to be semi-solid for the water to flow through it. Or the water gets so hot that by convection it rises back up where it's vented out at the seafloor, and that's what we see as a black smoker or a deep sea vent. With temperatures, I have 350 degrees Celsius there. That's an average temperature. The hottest one ever, I think, is 407, 406 degrees Celsius. Okay? So we have cold seawater reacting, changing in temperature and chemistry, and then coming back out the top where we can sample them. We have very limited ability to actually drill into the ocean crust. It's got major technical problems when you're drilling on Swiss cheese. So the hydrothermal vents, they start out as seawater, right, or 2 degrees Celsius seawater with 52 millimoles per liter of magnesium, and they end up looking totally chemically different. These reactions with the rock, with these heated rocks, change the chemistry of the seawater. Vent fluids have a pH of about 2 to 3. Seawater, being, average water, has a pH in the 7 to 8 range. Vent fluids have very high concentrations of metals: iron, copper, zinc. What else have we tried measuring? Cobalt, chrome, you name it. A lot of transition metals in there. And most exciting, vent fluids have high concentrations of hydrogen sulfide, stinky, rotten egg gas, toxic to humans. But again, remember, vent fluids have no magnesium. So somewhere in that process of the water sinking down and reacting with that hot rock, that magnesium is being taken into the rock and disappearing. That's the sink. That's where the magnesium is going. So here's a little table of comparison, just so you can once again see some of these concentrations. We already talked about the temperature and the pH. Potassium, one of the alkalis. Seawater potassium globally is about 10.1 millimoles per kilogram. Mid-ocean ridges ranges anywhere from 1.1 to over 50. Sulfide, hydrogen sulfide, there's no hydrogen sulfide in regular old seawater, not even in bottom seawater. Up to 19.5 millimoles per kilogram. That's a lot. That will knock you over from the smell. Chloride, good old trusty chloride. 545 millimoles per kilogram in average seawater. We have found vents with chlorides as low as 30 and as high as 1,245 moles per kilogram. So look at the variation, huge range in variation all around, higher and lower than seawater. Very little copper in seawater, up to 150 millimoles. And again, pick on magnesium here, 52 in seawater and 0 in vent fluid. Okay? We know now that vent fluid composition varies from site to site, place to place, and we also know that it varies over time. Here's a look at boron. Boron was one of the elements I studied, so I thought, well, we'll pick on boron a little bit. I looked at boron at sites East Pacific, the northern East Pacific rise, one place where there had been a recent volcanic eruption, one place where there had been no eruption, 17 degrees south on the southern East Pacific rise. Lucky Strike is the site out in the Mid-Atlantic Ridge, and Logachev is also a Mid-Atlantic Ridge site, but it's a kind of unusual, different type of rock site. So this is the concentration of boron in seawater, this line here. And you can see that most vent fluids, this shows the range of boron that I measured, ranges from about, little above 400, right around the seawater concentration, upwards of 600 micromoles. Pretty consistent, right? And then we have this, one flyer, Logachev, something weird going on there. So we know it's not just for boron. Other elements do this. They vary from site to site. So not only are we chemically different than seawater, we're also thermally different from seawater, right? We started with our 2 degrees Celsius water, and then we end up with 407 degrees Celsius water. That's hot. When that hot hydrothermal fluid comes plowing out up from the ocean floor, it hits ice-cold seawater. So you've gone from very reducing, very hot, to an oxic environment that's very cold. You can imagine that that's like a clash of chemistry that happens. And what happens is we get all these metal sulfides that precipitate, iron sulfide, zinc sulfide, copper sulfide. All that hydrogen sulfide that's in the vent fluid mixes with the metals in the cold seawater, and it starts to precipitate. That's what makes the smoke. We call it smoke, but it's actually particulates of minerals. These minerals actually can build chimneys, big chimneys, meters and meters of chimneys. I don't have any chimneys anymore. Too many moves later. They're kind of fragile and they fall apart. But we've taken lots of samples, and they're filled, the insides are filled with sparkly minerals, that chalcopyrite and pyrite that look like fool's gold. They're called fool's gold. Okay, and all of that's from the precipitation of metals and sulfur. We also know that the fluids boil. Okay? What's the boiling point of water? Oh, come on. 100 degrees Celsius, right? But that's at atmospheric conditions, not in the deep sea. We're in the pressure space of like from about 250 to about 400 bars. So the boiling point of temperature is much higher as your pressure increases. Well, we actually were lucky enough in 1998, we're on a cruise in the southern Pacific, and we actually sampled a vent that was right around the critical point of seawater and just over the temperature to make it, we know it was boiling. We had all the chemical evidence that suggested it was boiling in the subsurface, but we got the temperature finally. So that was very exciting. So we have fluids that are literally boiling water in the depths of the ocean crust. Okay, so this totally turned things upside down for chemists, for the geologists, and there's been work ongoing, finding more sites, analyzing more elements, more isotopes. What can we do? This is just a picture. These are the sampling bottles that we use. They're made out of titanium because they have to be able to withstand the pressure, the temperature, and the 350, 400 degree fluid that's flying out of there in a region that was named Hole to Hell and 9 degrees north on the East Pacific Rise. So this leads to a bunch of questions. What's going on? Chemical, physical, biological processes occurring within the oceanic crust where we can't see. How do they vary in time and space? How much water and rock are reacting? Like, what's the flow? What's the overall flow? And what is the magnitude of the chemical flux? How many chemicals are coming out? What volume? And how much heat is being stripped out of the volcanoes from these mid-ocean ridges? This is a relatively recent picture of all the sites that have now been discovered. Okay, the little red dots. The red dots are ones that I know have been discovered. The yellow dots are ones that they're either have some evidence or suspect that they're there. Okay, on to the biology. This is where we really wanted to go, right, for a biology seminar? Nobody expected the animals. Chemically, we expected that these things should exist. Nobody was counting on the animals. Living in the deep sea is not an easy place to live. Again, it's dark, it's cold, and you're living on an active volcano. Okay? What they found was the huge communities. There's no sunlight at the bottom of the sea. We can't photosynthesize at the bottom of the sea. There's just no light to do it. And what they found were that all these animals, the bottom of the food chain here is autotrophic bacteria, and now I guess archaea too, that can actually convert the sulfur, the reduced sulfide, into energy, and that's what flows the energy chain at the bottom of the sea. So we're using instead of photosynthesis, we're using chemosynthesis, chemical energy, microbes breaking down the hydrogen sulfide that's present in the vent fluid, using the CO2 that's present in seawater to make sugars and all the other biologically important components for animals. So the bacteria, where are they? They're on the rocks, they're in the animals, they're on the animals, they're everywhere. Every place they look, they find more and different and new types of bacteria. Some of the bacteria live by themselves and just do their own thing. Some of them have symbiotic relationships with larger critters so that the bacteria process the sulfide in order to allow the larger critters to live. These animals are taking the pressure, they're taking the temperatures they can't see, and to us this would be a totally toxic environment. That level of hydrogen sulfide would kill us rather quickly. The poster child of deep sea hot springs, the giant tube worm. Giant tube worms are only found in the Pacific sites. They can grow up to be 6 feet tall. Okay? 6 feet tall worm. Red, okay? They look like big lipstick tubes. They look a whole lot nicer when they're in the bottom of the sea. When people bring them up, they look gross. They sort of fall apart, okay? Most of the times, the tube worms stick their gills into the 30-degree water. They don't stick it in the 350-degree water. They'll get fried. So they're absorbing, and then they're also floating back and forth into the seawater. So they're absorbing chemicals out of the vent fluid itself and out of the seawater. But how are they getting any energy out of that? They're a worm. Okay? Well, they're actually a big bacteria bag. They have no stomachs. They have no mouth. Inside, they are filled with these bacteria that are able to pull off the chemosynthesis. It's a symbiotic relationship, right? You have your bacteria in here, and the bacteria convert the sulfide that's been sucked in through the plume of the worm, and we have a symbiotic relationship, and the worms can live. And clearly, they can grow to be gigantic. Much smaller, the alvanilla worms, they're like yay big, okay? But they're amazing because they've been found in water that's 80 degrees Celsius. I tried to get in touch with one of the biologists that worked on this to see if that's still the record, but I believe that's the highest record for an animal. 80 degrees Celsius, anything that can live above 80 degrees Celsius? Probably not. Yeah, they're in the hotter water. So they're little, they're kind of cool. They build these big mounds and have little star-shaped heads. Okay, same idea. Again, they have symbiotic bacteria that can feed off the sulfide. Shrimp. We find shrimp primarily in the Atlantic in huge swarms, not so much in the equatorial Pacific. Okay? The shrimp are eaten by the crabs and the fish that live there, and the shrimp themselves usually chow on the bacteria that are covering the mounds in mats. So you will find huge meter-high chimneys in the Atlantic that are just covered in shrimp. And the shrimp, that picture makes them look like they're like lobster size. The shrimp are like shrimp. Shrimpy, very shrimpy shrimp. And you don't want to eat them because they smell like sulfur and they're gross. Okay? There are fish. There are octopuses, purple octopuses we're seeing at the very first site. Zooarcid fish, these kind of bland-looking white fish, are circling around. Okay? They have eyes, but it's dark, so I'm not completely sure what the point is. But they can grow up to be 2 feet long, and they are predators. I have seen a fish go after a tube worm and take a chunk out of it. So they eat anything and everything. It's opportunistic, you know. Let's eat a tube worm or eat a shrimp, whatever's handy. Now that we've discovered all these animals, biologists have discovered not only all the animals, but also the bacteria. The questions that are coming up, why are some animals here and some animals there? How are they getting from one place to another with miles, huge? These vent sites are non-continuous, right? You might have a vent here and not have another vent for half a mile, or even if it's across the room. How does a worm that's anchored to the ground get over there to the new site? That's a problem. Okay? So these are the questions that the biologists are working on now, the biodistribution of these animals. The best studied site, and I'm almost done here, the best studied site in the world is the 9 degrees north site on the East Pacific Rise. Best studied in terms of geology, biology, and chemistry. Okay? Why? Well, because in 1991, by absolute chance, scientists Alvin and Alvin stumbled upon what looked to be a very fresh volcanic eruption. No one's actually ever been in the submersible and witnessed an eruption, because if they did, they probably wouldn't be back to tell about it. Okay? They figured, the geologists looked at the sediment cover, the temperatures, figured that the eruption had happened within days to weeks at most. Okay? The biological communities, the animals that had been living there that they'd seen by a towed camera sled just a few weeks prior, either weren't there or were run over by lava flows. They were burnt, crispy, and dead. It's a dangerous place to live. Okay, so where is 9 degrees north? Just to give you a little point of reference, here's Baja, the coast of Mexico. We're right here. Okay, and specifically, this was the eruption area. That was Hole to Hell that I showed you the picture of. And what they did when they just stumbled on this amazing discovery is they went through and they put all these biomarkers, I forget how many, there were like 150 biomarkers, little plastic tags, so that they could see after the eruption, where do the animals come back? And the tags are still out there for the most part. So that was 1991. They're still diving on 9 North because it's been just an amazing site to study. So here it is, 1991. This was the site that they dubbed Tuborn Barbecue. Brand new lava flow. Remember those pretty lipstick-looking worms? That's them. Run over by a lava flow. They got cooked. And literally they could see charred, they brought up samples, they were charred. From a chemical perspective, it's been really exciting. I mean, we've over a decade of data of sampling the exact same vents. We can go back to the exact same vents over and over and resample those same vents and see how the chemistry has changed. That's a whole nother hour or two lecture in and of itself. This has given huge insight to the deep sea chemistry, what goes on, what happens right after an eruption versus years, days, years after an eruption. And the biologists have been observing the biology re-establishing. It's back, unless it's erupted, and no one's told me. I don't think so. Okay, so we've seen how this biology community can rebuild after a major catastrophic event. This is just a little chemistry data, because I couldn't do a talk without some lithium involved, lithium being my favorite element. Okay, these are some of the samples that were taken from vents right at the time, right after the eruption, and generally these were samples that were taken up to 10 years after the eruption. So you can see how much the chemistry changed over time. Okay, lithium concentrations went way up, and as did chloride. But what's more telling from a biology point of view is what happened to the animals. Remember the biomarkers that I said, all those little plastic tags that were marked so the biologists could find their way back to each spot? This was biomarker 141. So this picture was taken in 1991. No animals left. The white things that look like snow is actually bacteria raining down. This was probably 1992. So a year after this, I think, is closer to probably 94, and then 1997, I think, was that picture. So these have been named the Rusty Riftia because they've gone rusty.
Students at TLU engage in high-impact educational experiences that include civic engagement, aesthetic expression, critical thinking, and a focus on intercultural knowledge in a community that welcomes the interplay of faith and reason.